plan for today, like many of our lectures, is we sort of cover a whole field just in one day. And so what we want to do now for this week, basically, is talk about very simple models of how neurons interact with each other. And these models aren't true models. You should think of them as just tools for thought, just little toy models for allowing you to reason about how large networks of neurons behave. And in order to kind of make a nice simple tool for thought that doesn't have a whole bunch of things sort of sticking off of it, mathematical things kind of sticking off of it, we have to sort of cut corners. And that's not a bad thing. So what does it mean when we say we have some kind of Hebbian learning? Where does that come from? There was a guy, Donald Hebb, who had this idea about activity circulating around in networks and how that might change the strength of the connections in a network. And in general, when people say Hebbian learning, what they mean is some kind of learning rule, so some kind of rule for changing the strength of connections between units or between neurons that depends on correlation. So some kind of rule that depends on correlation. So correlation dependent weight change. That's generally what people mean when they say a Hebbian learning rule. So what is correlation? So correlation is basically a dot product. It's just you take a bunch of pairs of things and multiply them by each other and then add them up. That's fundamentally what correlation means. And so take a bunch of samples. So you have two columns. So here's column 1 and column 2. So those are two variables. And so we'll take samples. So this variable, say this variable was 1, and then this one was -5, and then this one was -4, and this one was 3, and this one was 2 and 3, and this one was 5 and -2. So what you do a dot product between these two things. And so what does that mean? That means you multiply all these guys by each other, you get the result, and then you add it up. So here's an example of a negative correlation between these two variables. So this, if you multiply, that's -5 plus, -12 plus 6 plus -10. That's going to be a negative number. So that's a negative correlation. So this guy is an example negative correlation. But you could have a positive correlation if the numbers tended to be more of the same sign. So if they were, instead of, if it was 1 and 5, -4, -3, 2 and 3, -5, -2, that would be a positive correlation, because when you multiply the negative ones times each other, you get a positive. So that would be a positive correlation. But you could also have a zero correlation. And so what is a zero correlation? So a zero correlation is basically where the sum comes out to around 0. So that would be sometimes they were the opposite sign, sometimes they were the same sign. So that's fundamentally the mathematical definition of correlation. Is just a dot product between a bunch of samples from two different variables. You can think of this as a vector, and you're dot producting it with this vector, and the dot product is the correlation. So now what does that have to do with neurons? Like when you look at this, you go like, yeah, it doesn't really look much like a neuron. What is a neuron? Well, you've got the NMDA channel here, and here's a dendrite, and we've got you got sort of NMDA over here, and you got the AMPA channel over here, AMPA, And then you've got like vesicles, they release, they cause some calcium to get in, a whole bunch of stuff happens, and eventually somehow it affects the AMPA channel, and then it also, leaks out and somehow affects these vesicles. It's just an unholy mess. So we argue that was like this, very sort of like this in a very general way. And how is it like it? Well, when there's activity, when a spike comes down here, there's activity in the presynaptic, as indicated by the presence of glutamate, which was the neurotransmitter. And then when that glutamate binds, it binds to this guy too, under the conditions where this guy has been activated by somebody else. So here's somebody else activated this guy, a bunch of other ones. Then that indicates that this guy was active and this guy was active. And if they're both active, then that's like a positive correlation. And if they're positively correlated, you change the weight. So the problem is this, if we were trying to make a model of this, we would have millions of equations for how long it took the glutamate to get out of there. How does the NMDA, what's the Huxley-like dynamics of what's causing this NMDA channel to open? There's all these rate constants of all these phosphorylations that are somehow changing the AMPA channels and the nitric oxide synthase. And, it's just be this absolute nightmare of interacting concentration levels of calcium, glutamate, NMDA channels, how many AMPA channels were there, protein synthesis to make the synapse stronger. It's just like your eyeballs would bleed trying to sort of understand it. And so what are we doing with our simple Hebbian learning? What we're doing is we're crossing this out. Now, does it mean that that's wrong? No, that's actually the way it is. But what we're trying to do is understand how a very simple model based on this simple correlation, simple mathematical correlation, not the real correlation that happens in real NMDA Hebbian synapses, spike timing dependent plasticity. We'll just leave that off to the side. We know that's what's under there, but let's just try to understand, can we just understand how very simple correlation things like this work? So that's the goal for today. So let's start off with the simplest possible, just ridiculously simplest possible model that we could make, and that would be just starting off with let's draw some units over here. So here's some units. There's their output. And here's another guy. And we're just going to look at just one of these. And so this is the jth unit. So that's output j. So there's a whole bunch of output units, but we're just looking at one. And then we're going to look at the inputs coming to this guy. And so here's, some inputs coming to that guy. I'll just put 3 of them in there. And so now we've got, we have the weight. So here's the weight from unit I to unit J. So where's unit I? Well, unit I is this guy. Input I, 2 I's. So that's input I, so this is output J, and here's weight Ij, meaning the weight coming from input 1 to output J. But we've got a lot of other weights, and so here's another weight. This is the weight coming from some other unit. We'll just call this guy I other. Okay, so that's somebody else. That's somebody else. And so this is the input from unit other to unit j. So input unit other to output unit j. And we'll see why we'll sort of like have this other versus I. So this is a single input and some other input. There's a whole bunch of other inputs. So, there's a whole bunch of different j's. That refers to all these output units. There's a whole bunch of i's. That refers to input units. A whole bunch of others. I'll make a reason why we distinguished I from other in a second. Okay, so that's our simple network. It's just, but we still have to define like how does the network behave? Like, are there time constants in the network? So the first thing we're going to do is we're just going to say we have a linear sort of instantaneous network. So one of the problems is when we heard about Hodgkin-Huxley, the stuff's changing all the time. There's time constants. There's rate constant, forward rate constant, backward rate constant. All these things are time dependent. So we're gonna get rid of that. We're gonna get rid of that and just say that the way we and what about like current and voltage? You had like current and voltage and conductance. So we're just going to simplify that and say we just have activation. So it's not really current or voltage. It's just like, on one number. It's just activation. It's activation, and that activation just basically linearly adds up. I mean, you can just add it up. You don't have to worry about the Nernst potential. Like if you open the synapse and you happen to be at the Nernst potential, nothing happens. We're going to blow that away and just say when we activate an input, it's going to add a certain amount of activation to the output no matter what. That's the linear part. And so what are the equations for this? They're just extremely simple equations. So our input-output rule says the output of a unit is just equal to the sum over all the inputs, the sum over all the inputs of each input, whatever the number is, the activation, times the weight. So if you have like 5, for example, like 5 down here, and say the weight was 2, then this little piece that's adding, because you have to sum across the inputs, and so just the term for just one weight is just going to be 5 times 2 equals 10. And so you'll add 10 to whatever the thing is for all the rest of the inputs, because this says sum across all the inputs. Okay, so that's just a linear, just a simple sort of linear unit. So it just sums up all its inputs times their weights, and then that's the output. So now, so that's we call that sort of input-output rule. Input-output rule. So let me just close this for a second. Okay, so now we know how these units operate. Now we have to say, how do the weights change? And so the way the weights change is the second part, which is the update rule for the weights. And this is a Hebbian update rule. And so it says the way that you change the weight is basically just to multiply the input times the output. Input times output. So that's, and what is that? That's basically just this over here. So so what is correlation? It's just a multiplication. It's just many multiplications. So, after getting many inputs, you'll sort of you'll average out the sum of the correlation. But the way that you implement that for like a single event is just a multiplication. So that multiplication here is just the same as sort of multiplying two numbers from two columns, inputs and outputs, by each other. So the first thing you see when you look at this is that we could immediately rewrite this by just saying, well, what is the output? Well, the output is this thing. And so we could immediately rewrite this as, input I times the output. But what is the output? Well, the output is basically all the inputs times their weights. And so that's why we introduced this other. So here you could say, so other includes I, but it's mostly other. So there might be 1,000 weights. So there's one I and then 999 others, including the one other. There'll be 1,000 others, which includes I. So it includes I, but almost everything is due to the other. That's the important point. Okay, so we have this. I forgot to put the summation sign. So now we got to put the just this thing in there. And so what is that thing? It's the sum over all the other guys of all the other inputs, which includes I, times the weights from all the other inputs going to this unit. Okay, so that's our equation now, same equation. So when you look at so what does a Hebbian learning rule fundamentally do? Well, it looks at correlation between input and output, also known as multiplication. But then the second thing is, since output is in fact just the sum of all the other inputs times their weights, then fundamentally what it's looking at is it's more looking at the relationship between different inputs. That's fundamentally what's going on. And so what we could do to sort of make that clearer, we could sort of move this guy in. So if I move this guy, in here, what do I have to do if I move it in there? I also, I have to fix by divide by number of inputs. So if I divide this whole mess by the number of inputs and then insert this guy into the summation sign, then we can see, we can sort of get a feeling for how this update rule works. So basically, it works as the sum over all the other units, which includes I, but I is only 1 in 1,000, say. And what are we summing? We're summing basically the correlation of input I with every other unit. So that's a multiplication there. That's a correlation. It's basically a correlation. So a Hebb rule sort of breaks down really to the correlation between inputs. Even though officially a Hebbian learning is a correlation-dependent weight change in which you're correlating input here with output, is input and output correlated. That's what the NMDA channel does. In spite of that, because output depends on everybody else, like these guys, it depends on everybody else, what you're fundamentally doing is you're correlating the inputs with each other. That's what's actually driving a Hebbian learning rule. And then it's multiplied by, the weight from, the weights are in there too. It's multiplied by the weight between every other unit and the current unit that we're working on, the output unit. But then the whole thing has to be divided by the number of inputs because we stuck the I in there. So that's where is this taken from? Well, there's a lot of people that have done this, but I put some readings from a long time ago by this guy Linsker, who sort of did some modeling using this very simplified Hebbian learning rule. And so you can take a look at that. I'll just write down the final equation that he was actually using. So So what we could do is we could call, if we call sort of input I times input other, if we call that Q I other, that's what he uses in the paper. So for correlation. So just the correlation between a pair of inputs, that's basically what that is. Then when you write the final equation that he used, I'll explain why it looks this way. Ij, this is about the simplest possible equation that you could have for a Hebbian rule. It's got a couple constants in it, and we'll find out what those are. So basically it's the sum over all the other units of the correlation between each, between the current unit and every other unit. But then there's another constant in here, which we need for it sort of being able to adjust things. And then that whole thing times the weight from other to j. And then divided by the number of inputs. And that was just because we stuck this I inside here. Okay, so that's our final equation. And we're just trying to see, like, what is, given various patterns of inputs, what does an equation like this lead to? So again, I just want to sort of emphasize absolutely how ridiculously oversimplified this is compared to real life. So what do? We don't have any time in the network. All we do is we stick a pattern into the network down here. So you apply a pattern. So here's the, here's an input pattern. What does that mean? It just means, it means a whole set of numbers, like 3, 2, 7, 0, 5, ... That's an input pattern. And then we calculate the output here, insert that output into how we're going to change that weight, and then we change that weight. So there's no time, like if you apply an input pattern, this thing doesn't sort of like change activity. You just basically apply an input pattern, calculate the output, you're done. It doesn't, there's no time course. It doesn't sort of like fire for a little while or anything like that. It's just sort of an instantaneous thing. Like you apply an input, you get an output, you're done. You apply another input, get another output, change the weights, you're done. So that's the absolutely simplest model we could make of how a network works. So what does that mean? So what does that mean in terms of like, say like an image or something? So what if, we had some kind of, like say you would be training a network to recognize faces, something like that. What's kind of, just to make this less abstract, what kind of thing are we talking about? Well, imagine your input layer is like this, and it's got, there's a fine grid of units. So there's a unit at each one of these little crosses. And say here's an output unit, and all these guys project up and have weights onto that output unit. So you imagine you have like a retina, and all these guys sort of project up there. Okay, so how would you train a network like this? Well, show it a face. So here's a face. And then what do? Well, the face is an input. And so what is the input of the face? Well, it's, this pixel and this pixel on, this pixel on. There'll be, this pixel is on. So there'd be like a whole bunch of pixels here on that represent the face. This guy's on. Here's the edge of the face. Maybe those guys are on. So you'd have a pattern. That would be this input pattern. You have some numbers across all the pixels. A lot of them would be 0. This guy would be 0 out here. It's just off in the background. And then what you do is you just run this equation and change all those weights. And then stick another face on, run this equation, change all the weights. So it's a very simple model, simplest model we could possibly think of. So what is that going to do? So fundamentally, just think of it intuitively, what's that going to do? Well, if there's a correlation between two units, like for instance, say the eye units are correlated with the mouth units. Since those are correlated, those eye and mouth units' weights are going to get bigger. That's fundamentally how a Hebbian learning network works. It looks out at the input. So you can put yourself here, you look out at your inputs, you say to your inputs, like, how correlated are you? If you're correlated, you're going to add to the sum and make the weight go up. And so basically, if two inputs come in that are correlated across many faces, like eyes and mouth are correlated across many faces, you're going to turn up the weights coming from those units and make this unit up here more sensitive to faces. You make it into a face detector because it just amplifies correlations between input lines. So that's really the simple, very simple sort of way of thinking about what a Hebbian learning rule will do. And so what we want to do now for the second half is to go over a very simple example of a Hebbian learning network where we combine some maps with it. And so where did maps come from? So it turns out, if you look at the brain, what is the first principal component of brain organization? So if you had to say, like, I look out at the brain, and what is the basic, at the level of, like, bunches of neurons connecting to other neurons, what is the most basic principle of how the brain is hooked up? And for that, you would have to say maps. So there's maps all over the brain. So an example is the retina projects into the lateral geniculate. We haven't talked about it yet, but that's a structure in the visual system. It projects in there with a map. The lateral geniculate projects to V1. It projects from V1. The projection from lateral geniculate to the V1 is in a map-like way, where neighbors sort of project to similar parts up in the visual cortex. If you look in the basal ganglia, the dopaminergic projection, down, that's coming from the substantia nigra going up to the striatum is topographic. There's a map in that. So virtually anywhere where you look in the brain, there's a map. And so how can we sort of characterize that? Well, one very simple cartoon of how a map works is that, imagine we've got two layers of units. And so here's a unit down here. And when what does it mean to project to another area as a map? Well, what it means is you go up to the similar part of layer 2. So here's like layer 1 and layer 2. So you go up to a similar part of layer 2, and you project strongly to that point, and then as you move away from that point, it falls off. And so we could describe your probability of connecting as something like that. So what that means is that this guy will, there'll be a lot of connections right to the middle, and then as you go off to the side, there'll be less. And then it's the same for every other unit. So every other unit will be the same. So if you go over to a nearby unit, it'll be the same thing, but the curve will move over a little bit. So that's what it means to have a map-like projection. It's not a one-to-one, it's one-to-many, like 1 to 1,000, but it's organized in a way that neighbors down here sort of project to neighboring parts up here. That's the definition of our topological map, sort of a topographic map between two things. Now, there's two ways of looking at this. We can sort of look at it from this point of view, and we're going to use both of them. So that's why I want to introduce it here. So this is sort of the feed-forward way of looking at it. We'll call that feed-forward. But another way of looking at it is the way that I started off with, which is another legitimate way of looking at it, is let's take one guy here, and who connects? So what does this imply? Well, this implies that if you went down to the equivalent part down here, what's going to happen is there'll be a strong connection, coming up to this guy from over here. And then as you move off to the side, there's still a pretty strong connection. And as you get further off to the side, there's less of a chance you'll hook up. And so what we could look at this instead is, what is the probability that you got input from this part of the map? That's sort of just, it's the same data, same architecture, it's just two different ways of looking at it. And this way of looking at it, we could call this the receptive field. It's the receptive field for this unit. It's just like, what can this unit see in the input? Okay, so let's assume we have something like that. We've got all these layers. And we'll talk about receptive field many times. Receptive field is like, I go to a unit and just find out what connects to it, but connects as input to it. But you could look at it the other way. I go to a unit down here and see which what output units it connects to. So those are equivalent ways of thinking about the network. And so let's keep those both in mind. Okay, so now what we want to do is what is kind of the overall goal of this model? So the overall goal of this model was, we could look at something like putting faces on the network and trying to train the network on faces, but let's just assume that we have some maps and we've got a Hebbian learning rule and we apply noise down here. So start with noise. And what is the idea? The idea is, when the organism is developing, the embryo is developing, it's got neurons, it's got maps, but it's not seeing anything. It's hearing things, but it's not seeing anything. And so let's just assume that we've got some random firing in the retina, for instance. It turns out it's actually not random, but let's just assume we had random firing. And so assuming that we've got maps, what kind of weight structures do we get if we just start off with noise and filter it through a whole bunch of maps? That's really what we're going to try to develop here. So let's start off with we'll sort of look at it in this feed forward view first. So say we have a something like this. Feedback. Let's look at it in the receptive field view. And so we've got, a whole bunch of units here that project up to this guy, and there's less off to the side. And now let's just apply noise down here, and then change the weights. Apply noise. And so what is noise? Well, noise is, what does it look like? Well, I looked at my video from last year. I said, yeah, back in the day when we had to walk 10 miles through the snow and we had actual TVs that had antennas, if you turned to a station that didn't exist, you would see noise. And what is noise? Noise is just like different random pixels just coming on randomly. It just kind of looks like snow, or just like some sort of background noise. But what does it mean? What does it really mean in terms of when you say noise? Usually what you mean is something with zero correlation. That's what you mean by noise. So apply noise, but what does that? That means the correlation between two parts of the signal equals zero. And what does that mean? That means that if you go to this number, and then get a whole bunch of samples of that, do the correlation calculation, you get zero. And if you go to this one and this one, you get zero. All possible pairs are zero. And what does that look like visually? It just looks like a whole series of random dots that could be dark or light. So if we apply that, and that's kind of like the simplest thing you could imagine, that could just occur like, some neurons just firing, background firing of neurons, just randomly firing. So what happens to this guy? Well, nothing incredibly interesting, but basically all weights go all on or all off. And so now you might wonder, what does all on or all off mean? Well, one of the things that we had to do here to cut corners is that we had to say these equations don't have any limits on them. If you look at these equations, you can see they don't have any limits on them. So if two things are correlated, if two inputs to a unit are correlated, that will continue to drive the weight up forever. And so we had to do one more thing here. So, so we have to calculate the change in weight and then clamp it. So calculate change in weight, use it, or clamp to max minimum. So in real life, what does this? Well, if you have a synapse and you potentiate it, the synapse gets stronger, it gets more AMPA channels, but eventually, there's a maximum number of AMPA channels you can stuff into a synapse, and so then that's it. That's the strongest the synapse can get. This simple equation doesn't have that in it. That would be a whole other set of equations where that sort of dies off as the synapse gets stronger. And so to sort of like just do a real simple version of this, we say, okay, we'll just do it this way, and if you run into the limit of your weight, then you can't get any higher. So that's that's to deal with the fact that our equations are crappy. Our equations are just like super simple, nothing like a real synapse with NMDA and limited resources at the synapse. Okay, so what will happen here? So basically you just turn all the weights on or off. Now that sort of seems kind of uninteresting, but there's a point here. So so this is the first layer and the second layer. If we now look at what kind of a correlation we get, so now let's look at it from the feed-forward view. So we looked at it from the receptive field view, but now let's look at it from the feed-forward view and try to figure out what kind of correlation we get up here, because that's going to drive the next layer. So if you look at the kind of correlation, well, you've got a unit here, and it projects, strongly to units that are right above it, and less strongly to units that are off to the side. And so what does that do? So this is unit 1 and unit 2. So what kind of correlation do we get up here? Q. So basically we put noise in down here with no structure, and what we get out is noise that has some correlation. So this is output has correlation with neighbors. So the output, the output Q is correlation with neighbors. So what does that mean? What would that look like in an image? Well, what it would look like in an image would be, instead of just these random sort of like dots, what would happen is in your image, you'd instead get something that looked like nearby guys would be on or off. So you would get little blobs, and they would go in all different places, but you would get little blobby looking, little cloud looking things. And so the important point is that, so what caused that? Well, it's just, it's the structure of the connections, the structure of these map connections caused it, but now we've got a different correlation here. And so now we can say, okay, so what will happen if we now take that as an input and apply it to the next layer? What's going to happen, when we go up one more layer? So I'll erase this side. So what happens then is you have the possibility of getting center surround structures, which are commonly found in the nervous system. And so what is, why does that occur? So now let's assume that we applied to our input. So now here's our input layer 2 and 3. So now we're applying this kind of correlation to the input instead of noise, because that's what we calculated what would happen if you just turned all the weights on. We'll just consider the on case. So now what happens? Well, now what will happen, we still have the same connection pattern. So we haven't messed with the connection pattern. So what is the connection pattern? The connection pattern is these guys have it, if they're in the same part, they have a tendency to make a strong connection. And if they're off to the side, they have a tendency to make a less strong connection. Some still connect, but there's less chance of them connecting. Okay, and now, so what is this? There's two patterns of things there's two different Gaussians we have to consider here. So one is this Gaussian. That's the connection Gaussian. Connection probability. But we also have this guy. So this guy is the correlation probability, okay? So we've got two of them. This guy's a little bigger. And so what is going to happen if we stimulate with that? So what's going to happen is, so remember that these guys, what does this correlation pattern mean? It's the same for every part of this input layer. So that means like these guys are correlated with these guys. But these guys are correlated with their neighbors. These guys don't connect to this guy, but they're correlated. They connect more to the ones that are above them. So these guys are correlated with their neighbors, and these guys are correlated with their neighbors. So everybody's correlated with their neighbors. But if we're looking at this output unit, most of these guys are not going to connect. So what will that do? So here's the important way of thinking about what Hebbian learning does. What Hebbian learning does is it's going to somehow focus on these synapses that come from the center where the guys are correlated, because this correlation is what drives the weights up. And so the weights in the center of the receptive field, that you can think of this as the receptive field, are going to get a leg up over these guys, because these guys are correlated with their neighbors, but their neighbors don't connect, and so then it won't drive the weight up. It won't drive that weight up, but these weights will get driven up. So what that can result from, so say we have something in here that these other constants that say drive all the weights down. So if everybody gets driven down, if the center weights have a leg up over these guys, they can be positive and the neighbors can be punished and be negative. And so you'll get a center surround type structure. So is this how center surround structures are made? We don't know. But let's just look at that from the feed forward point of view. So this is the receptive field view, and this is the feed forward view. So say we had some kind of center surround structure generated, then what's going to happen is these guys are going to have positive weights to the center, because those guys got the leg up, and then it will have negative weights over here. And so what you'll get, the kind of correlation pattern you'll get, instead of just sort of a positive blob, you'll get something that sort of looks like this. So basically, we call that center surround. So what that means is, and what does that look like in a picture? Well, what it looks like in a picture is there'd be some positive things in the picture, but then if you go out a little distance away, there's some negative ones. And then, the next time point, it's somewhere else. But at an instant in time, you would see this tendency for there to be negative things that are, sort of positive. So close neighbors are positive, slightly further away neighbors are negative, and then if you're far enough away, it doesn't matter, you'd be uncorrelated. So this is the Q, the output that you get from a center surround layer. So finally, we've got to Now, if you look at that, it just sort of seems kind of boring, like, who cares about center surround? That's kind of a low-level thing. But when people did experiments on animals, they discovered that when the animal first opens its eyes, before it's seen anything at all, it's known that it has neurons that are sensitive to orientation. There are orientation selective neurons from the instant the animal opens its eyes. And so somehow the system has wired up orientation selectivity before the animal has actually seen anything. So it doesn't require actually sort of experience with real objects. You already have something that detects edges, detects the orientation of contours. It's already there. So people have had various ideas about how that might be created. But a very interesting possibility is that if we look at this kind of correlation pattern that we get in layer 3 and assume that we've got that correlation pattern as an input correlation pattern, what do you get in a higher layer? And so it turns out you can get orientation selectivity. So now we've got to draw it out as 2D. So this is our layer 3. So we've got, say you've got some units in layer 3, and they're basically strongly correlated with their neighbors, positively correlated, and then slightly further away neighbors are a little less correlated, are negatively correlated, and then far away neighbors are uncorrelated. So, positive, negative, uncorrelated. And then you've got another guy over here, and it's got the same thing. And another guy over here, it's got the same thing. So everybody in this input layer has a center surround type correlation. So that's our, and we're assuming that came from the fact that when we went from layer 2 to 3, the center weights got the leg up, and that sort of generated a center surround structure. And then when you feed in noise to the bottom, it turns into like sort of blobs in layer 2, and then it turns into these blobs with a surround in layer 3. So that's layer 3. Now we have to consider, what happens to a unit up here. So here's a unit up here, and then all these guys are projecting up to it. Now you can start to see, wow, this is a little more complicated to try to guess what's going to happen up there. So what actually happens? Well, it turns out if the units are very far away from each other, like this, where there's zero correlation, then nothing happens, right? So those weights won't be driven up because these guys won't be correlated with each other. But if we get a little closer, so say something like this, those two units are actually going to be negatively correlated with each other. So this is, Q equals 0. This is Q equals negative. Because you can sort of think of the positive part of this guy is over the negative part of that guy. It's one way of sort of thinking about it. If you're sort of at an intermediate distance away, you're going to have a negative correlation here. And then as you go farther away, you got 0. And then if you get really close, where you can sort of think of those two center surround guys sort of mostly overlapping, then negative will correlate with negative and positive with positive. And these two guys will be positively correlated. But you can see now we've got a problem because it's kind of advantageous to get people kind of close like this, but as soon as you pull them apart a little bit, they start sort of trying to drive the weights down. So you can see there's like a push and pull. And so what ends up happening? Well, it turns out that arrangements of the units that are sort of like this, like sort of in a triangle from each other, are slightly less correlated than cases where you line up units in a row. Because here you can sort of see the surrounds the surrounds are messing up in the middle, but the centers are lined up there. And so it turns out the correlation, so this is the correlation between these units when you've got an input layer that has center surround. the correlation, it's slightly higher for linear structures. But it turns out, it's just as good to have a linear structure going this way. Linear structure, etc. So there could be many different orientations. And what are those? Those are like Hubel and Wiesel orientation detectors. And so the idea, sort of like, just to sort of back off in the last minute now, so what's the point of all this mess? So obviously, we haven't seen anything. We're not learning about faces. We're not sort of like doing anything like that. All we're saying is, if you have the simplest possible Hebbian network, what is the implications? The implications are, it looks out at the input, and it turns up the weights from things that are correlated. That's fundamentally what it does. What does that do if we start with junk? We just start with random noise. Well, if you run it through a bunch of layers of maps, what you end up with is orientation detectors. You just self-assemble these orientation detectors. They'll be sort of like at random orientations. For every next unit in this thing will just sort of pick some random orientation. The real thing isn't like that. It's got orientation columns, etc. But forget it. Forget about that for the time being, and just think that what we're doing is we're bootstrapping the system so that when the animal opens its eyes, it's already got an array of orientation detectors, and it can start filtering actual real objects in the world. And it's important to keep in mind that if you don't have a world there, the visual system will not work. So if you raise an animal in the dark, or if you look at a human that had congenital cataracts that cause everything to be incredibly blurry so that they don't see any actual objects in the world, the visual system in those animals or people will be permanently damaged. It will get into a state where it doesn't work. And so the visual system during development absolutely relies for its connection pattern on the fact that there's a world there. If there isn't a world there, it's not going to work, and it will be permanently messed up. So a lot of information is not in the genes to wire things up. It just, a lot of information comes from actually seeing the world, seeing the mother wildebeest, and seeing little movements of the world as you run across the plain. So at that point, obviously, we could start to learn about how the world is, how are objects in the world, how does the light hit different objects in the world, things that couldn't possibly be coded genetically. But the point here is that it's not a blank slate when you start off. There's some genes that create these maps, and then you've got activity circulating through all these maps, and it can generate these kinds of structures in maps that can then be very useful when you actually start seeing real things. So you see real things, you immediately filter them by orientation, and then you can sort of eventually attach contours together and do all different kinds of higher level things once you see real objects. So that's kind of the story here. There are simple Hebbian learning. So you start off with, the output is just the inputs times all their weights. The change in the weight is input times output, but that can be rewritten as the change in weight equals one input times the sum of all the other outputs and their weights, times their weights. And we can think of that, another way of thinking of that is that the change in weight equals the 2-point correlation between this unit and all the other units times the weights. Okay, so I heard the knock, so we'll end there.